And so this is what we wanted, right? That's what we kind of started with, was we said, well, we want to make this change, but we need to then include what's over here. Otherwise, we'll lose the sense of how concentration changes when we start looking at how chi changes with zeta. So we actually need to evaluate all of these terms on the right. We'll keep these terms here, and then we can make a replacement with the second order concentration gradient in y. So d squared Ca dy squared equals, so this is d squared chi d zeta squared, times, we can evaluate this, d zeta dy. The change in zeta with respect to y is 1 over L. We actually have another d zeta dy here. That's going to be 1 over L also, 1 over L squared. dCA dx. We're actually going to need to solve this for the concentration as a function of chi. So dCA dx, I said, but dCA d chi. So we need to solve this for the concentration, and it'll be chi times KEQ Ca naught. So if we take dC d chi, it's going to be KEQ Ca naught. But let me write it. So I'm going to solve this function for Ca. All right, now we know KEQ and Ca naught are both the constants. I can now take dCA d chi and find out that's KEQ times Ca naught. All right, so I needed to include this in order to be able to make the link from chi and zeta back to C and Y. So if I want to replace into my original equation here, excuse me, we wanted to replace this, and we know then we can replace it with this. We have d squared chi d zeta squared times KEQ Ca naught over L squared. All right, and then we have minus K double prime Ca all over diffusion of A through B equal to 0.